Now we'll see the effect of the external load, but first of all we have the first figure represent here the nut in contact with the member. Then we apply the torque here. Because of the torque, the force developed in the nut will be tension that we called as Fi, and the member will come in compression. And the compression force we can show inward. This value is also equal to Fi. So compression force is inward. There is a compression of the material by value equal to delta m. So from this point the length has been decreased by delta m, and the length of the nut will increase, that equal to delta b. And we are knowing here that value of delta b is same as initial load Fi divided by the stiffness of the bolt equal to Kb, and the value of delta m is same as equal to Fi divided by the stiffness of the material, which consists of the top washer plus we have bottom washer plus material A and B. Now we'll apply here the external load. So this time the assembly is formed, that is these together will work as one single unit. So let's say we have external load equal to P, and this external load is a tensile in nature. Whenever we have a tensile force, then you have to show the value of force in an outward direction. So this is the entire assembly, and because of P, which one is the external load, is in tension, so length of the assembly will going to increase. So there is an increase in the length of member by delta m, and there is also increase, corresponding increase is remain same because this one is a single assembly, and we have this value is same as equal to delta of bolt. So we introduce here the external force is equal to P, which is tensile in nature. This force that affect the member rather than affecting directly the bolt. The load will elongate the bolt even further from the previous position by amount equal to delta B. At the same time, it elongate the member also by an amount equal to delta m. Because it is a complete one assembly, we can claim here that the value of delta m is same as equal to delta B. And again we can write the value of delta m using the stiffness formula. So every time you have to write down the value of delta as force divided by stiffness. So delta m we can write as force in the member Pm divided by the stiffness of the member Km is same as equal to the force in the bolt divided by the stiffness in the bolt. So when the external load is applied, in that case the load will elongate the bolt even further by amount equal to delta B. At the same time, the member will get elongated by delta m. Because in contact we can claim here the value of delta m is same as equal to delta B. This one is just a model here in which the two springs are in parallel. So one stiffness we have to show for bolt and one stiffness you have to show for the member. I will show here equivalent figure. So we can represent here one spring for the bolt, one spring for the member, that equal to Km, and here we have applied the force that equal to P. So this one is again an external force is applied, P, which is in tension. Because of this there is an equal deflection of both. So this value is same as equal to delta of bolt, and this value is equal to delta of material. So if you cut at this point, then we can develop the BD here. We have vertical force is equal to P. Seeing here the spring is get stretched, for spring the force will act inward is same as equal to Kb multiplied by its deflection will be delta B. This spring is also get stretched, so the spring will try to attain the original position and it will develop a force that equal to Km into delta m. So here P is the external tensile load and the part of P is taken by the member and taken by the bolt. Now this value of product of KB into delta B is given as PB value, which is the portion of the P taken by the bolt, and this value we'll call it as PM, that is a portion of the P which is taken by the member. So in this case we have P is equal to PM plus PB. Now finally we are left here two equations. One is PM upon Km is same as PB upon KB, and we have value of P is equal to PM plus PB. So we can solve here either in terms of PM or in terms of PB. So here I will solve for PM. In that case I will get PM. So we have Km divided by KB, Km divided by KB multiplied by PB. And this substitution will do in this equation. In that case we'll get PM is replaced as Km divided by KB multiplied by PB plus we have PB. PB can be taken common, so we have P is equal to Km plus KB divided by the stiffness of the bolt KB multiplied by PB, where P is the external load and PB is the portion of the P taken by the bolt. So we have a P is the external load, that is the tensile load, part of which will go into the bolt, that equal to PB, part of it will go to the member equal to PM, and because of the assembly and the applied external load is equal to P, we have equal deformation of the member and the bolt. So we can generate a relation here that we have PM is equal to PB into Km by KB, and similarly we have P is equal to PM plus KB. We have final equation is P is equal to PB into Km plus KB upon KB. From this one we can calculate the value of PB as well as the value of Km. Fi represent here the initial load, and this initial load is a negative value in the case of member and is a positive value in the case of bolt. We already discussed this graph here. Here delta B is a deflection of the bolt, delta M is a deflection of the member. Here delta M will be taken as a compression because it is plotted on the left hand side, and delta B is taken as the tension because it is plotted on the right hand side. This value of Fi will be equal to Km multiplied by delta M. You have to treat this value as a negative value, and the value of Fi is equal to Kb multiplied by delta B. You have to take as positive value. And when the external load is added, then we can calculate the contribution of PB and the contribution of PM. So these are the additional load that will come in addition to Fi on the bolt and gasket. So that additional deflection we have to show in the figure. The total load goes into the bolt will represent as FB will be equal to the initial load Fi plus PB, which one is a portion of the P taken by the bolt, that equal to PB. Because of the external force P, the bolt as well as member both will deform by equal amount equal to delta B and delta M. So that value additionally you have to show on the right hand side. So this value is same as delta B. Then draw the projection on the stiffness line of the bolt, that is this vertical distance will be same as equal to PB, which we are writing as the stiffness of the bolt multiplied by delta. So this additional load is come on the bolt. Initial load is Fi. So if I draw the horizontal line from the extra load that equal to PB, then this value represents here the total load equal to FB. So this total load FB is nothing but Fi plus PB. So this value is same as equal to Fi plus PB. PB is same as equal to P multiplied by KB divided by Km plus KB. In this fashion we can calculate the total load that goes into the bolt. So total load that goes into the member will be written as Fm and is same as equal to the portion of the load which is taken by the member equal to PM minus, because we have taken here the initial load for the member as compression, so basically it's a plus and minus Fi. So final equation is same as equal to Pm minus Fi. But when the external load is applied here, the member is also get elongated. So this member is get elongated by an equal amount that equal to delta M. So we can project a perpendicular again from this point. If I project a perpendicular from this point, then I can look at the value on the graph. Then this vertical distance here between the Fi and this line will be equal to Pm. And so we have Pm minus Fi will be the force in the member, which represents here the total load that goes into the member, which is a contribution of the initial load plus Pm. So quickly summarize what we have done here. Let's say P is the external tensile load. Part of P is taken by the member and the bolt. So we can write here the value of P is same as equal to the sum of PB, that is the portion of the P taken by the bolt, plus PM, that is the portion of the P taken by the member. After initial tightening, the assembly will work as a single unit, and therefore we have delta M is same as equal to delta B is same as equal to del delta. That is the extension due to the external load P of the assembly. So we can write here the value of P is equal to the stiffness of the bolt equal to Kb multiplied by del delta plus stiffness of the material is Km multiplied by del delta. Or we can write the value of P as del delta multiplied by Kb plus V of Km, that is the stiffness of material. So we are able to calculate here the total deformation due to external load, that is del delta, which is nothing but P divided by the sum of the stiffness of the bolt plus stiffness of the material. Fi represent here the initial load, and in the case of bolt, you have to take the positive value of Fi because it is in tension. And for member, you have to take it as a negative value because it's a compression. So out of the external load P, Pb represent here the portion of the P taken by the bolt. In that case, we can write the value of Pb as, since we have delta M is same as delta B is equal to del delta. So we can write the Pb is equal to Kb multiplied by del delta. And we can calculate del delta as P upon Kb plus Km. And Pm value we can write as the stiffness of material multiplied by del delta. So anytime you want to calculate here the total load that goes into the bolt, which is nothing but Pb plus Fi, that is the initial load. As far as the bolt is considered, Fi is positive value, and we can replace the Pb value as Kb multiplied by del delta. So we have initial load is equal to Fi plus Pb value is equal to Kb multiplied by del delta. And we can replace del delta as P upon Kb plus Km. Similarly, out of the external load P, Pm will be the portion of the P taken by the member, and for member Fi is a negative value because of compression. So total load that goes into the member is Fm is equal to Pm minus Fi. Here we can replace Pm is equal to Km multiplied by del delta. So we have Km multiplied by del delta minus Fi, and del delta you have to calculate as P upon Kb plus Km. So remember this equation, that is total deflection will be equal to P divided by Kb plus Km. Fb will be equal to Fi plus Pb. Pb will be same as Kb into del delta, and Fm will be equal to Pm minus Fi. Sometimes you have to find out the condition for the easy removal of a gasket, that is a material, or there is no clearance between the component, or for leak proof joint. In that case, we can force the value of Fm equal to 0. So we have Fm is equal to Km multiplied by del delta minus Fi. You have to make this value equal to 0. Or we have the initial load Fi should be equal to Km multiplied by del delta, and we can replace the value of del delta as P upon Kb plus Km. So this time we'll get the equation as Km upon Km plus Kb multiplied by external force equal to P. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.